In our first example, we have that a boat weighs 32,000 pounds. Its motor provides a thrust of 5,000 pounds. We have the water resistance 100 pounds for each foot per second of the speed v of the boat. And then we're told that the rate that the speed of the boat is changing with respect to time can be modeled by this equation. If the boat starts from rest, so from that we can assume that when time is equal to 0, velocity is also equal to 0. What is the maximum velocity that it can attain? So here we know we need to find the equation that represents velocity as a function of time, and then 2, consider as t goes to infinity, what is the behavior of v? And once we've been able to do those two things, we'll have answered our question. So I think the first thing that we'll want to do is let's divide both sides by 1,000 to simplify our expression. And we'll get dv dt equals 0.5 minus, and really quick, I thought this was 500, not 5,000. 5,000 divided by 1,000 should give me 5, minus 0.1 v. Now this is a nice separable differential equation. We see if I divide both sides by what's on the right side of the equation, I'm going to get something that I know how to integrate. It's going to be the integral of natural log with a small u substitution. So I'll divide both sides by that. And then we can integrate both sides with respect to t. Now let's go through the u substitution just for practice. U is 5 minus 0.1 v. Du would then be negative 0.1 dv. We see we just have a singular dv, so we're going to divide both sides by our negative 0.1. So our integral after u substitution is negative 1 over 0.1, the integral of 1 over u du. Now negative 1 divided by 0.1 will give us negative 10. Natural log absolute value of u equals t plus c, and then our u gets replaced. At this moment I'm going to divide both sides by our negative 10 as well. Dividing our constant of integration c by negative 10 isn't going to change the fact that it's a undetermined constant, so we can just leave it as plus c. No need to write it as minus c over 10. Now we know our goal is to get the velocity equation by itself. Even now, we could consider what happens as t goes to infinity. We could reason about what's happening to v, and let's do that first, just so y'all can see how you can, even in this implicit form of the equation, understand what's going on. And then after we do that, we'll go through the process of, okay, if I isolate for v, then how do I reason about the maximum velocity? So as t goes to infinity over here, think about negative 1/10 times t plus some unknown constant. The unknown constant is not affecting anything significantly as t goes to infinity. So we're basically asking ourselves, what happens to negative 1/10 times something going towards infinity? Well, it's going to be going to negative infinity. And then what's the left side doing? It's natural log of this expression. Well, recalling back our graph of natural log, we see that natural log of x goes to negative infinity as the input x goes to 0, particularly 0 from the right. Now our equation is not just natural log of x, it's natural log of this. It's a composition of something more complicated. So we know the left side will equal the right side. As t goes to infinity, this goes to negative infinity. And then that will only happen if this interior goes to 0, because natural log of something getting closer and closer to 0 approaches negative infinity. So we're asked to figure out when is this getting close to 0 or equaling 0, approaching 0 as a limit. So we can solve this, add the 0.1v over to both sides, divide by 0.1, and we should get 50. So that means our maximum velocity, no matter how much time passes, the maximum velocity will be 50, and then let's look back at the units described. Feet per second. So in this way, I've answered the question that was posed without having to go through the trouble of rewriting my expression and isolating for the dependent variable v. However, I still could have approached the problem if I had solved the equation first to get v by itself. So let's do that as just an alternate method. Okay, so at this point I'm looking back at my equation, and I'm going to try to get v by itself. I'll do that by raising both sides of this expression, e to both sides. E to the natural log cancels out and it leaves us just with our input. E to this expression. Now, whenever you're adding things in the exponent, remember e to the a plus b is equal to the e to the a times e to the b from our pre-calculus knowledge. So this will end up being on the right side e to the negative 1/10 t times e to the c. C is an unknown constant. E to a constant is still a constant. So often we will just more simply write this as c times e to the negative 1/10 t. And now we know c is always positive. E to something is also always positive. So here we can feel confident that we're going to drop these absolute value bars, and we can isolate to get v by itself. So here I'm going to add the 0.1v over, subtract the c e to the negative 1/10 over, and we get 5 minus c e to the negative 1/10 t equals 0.1 v. Divide both sides by 0.1. V equals 50 minus c times e to the negative 1/10 t all over 0.1. And the point of this question was to figure out the maximum velocity. So again, we consider what happens as t goes to infinity. Well, as t goes to infinity, we have e going to negative infinity because of this negative. 1/10 times infinity goes to infinity, but then since we're multiplying by the negative, we're really looking at e going to negative infinity, and that's the idea of 1 over e to the x, the limit as x goes to 0. Well, what happens is whenever the denominator, the top is is fixed at 1, the denominator is exploding in growth, that's going to make the overall fraction go to 0. So we see as t goes to infinity, this part of the expression goes to 0, and we're left with 50 minus something approaching 0, so our velocity approaches 50 feet per second, just as we found using our other method. Now, some of our acceleration and velocity problems will involve circumstances where we have resistance that is proportional to the velocity. Imagine a body in motion, and particularly it has vertical motion, so straight up and down. It has mass m near the surface of the Earth. That body in motion is subject to two forces. The force of gravity, which is the downward gravitational force, and the force of the air resistance, proportional velocity, and one thing to note is this will be directed opposite the direction of motion. So if the object's traveling down to the Earth, the air resistance force will oppose it being an upward force. So the net force on the object can be found by adding these two forces together, which ends up giving us negative k times the velocity of the object minus the mass times gravity. Newton's law of motion, force equals mass times the derivative velocity over time, can then be isolated to get dv dt by itself, so we're going to divide both sides of this equation by m, and when we do so, we get dv dt for these situations is negative rho v minus the gravitational force. Now this rho is going to be a constant dependent on the problem we're working with. So as we look through this next example, 36, it says consider an arrow shot straight upward with the initial velocity of 49 meters per second from the ground. So when they tell us from the ground, we know our initial position is also 0. Now the air resistance that we're going to consider gives us a rho of 0.4. Find the maximum height. Now one thing to keep in mind is if we are shooting something into the air, its maximum height will correspond to when the velocity is equal to 0. Once we know when the velocity is equal to 0, solve that for t, then we can plug that value in into the position function that we can get by just integrating our velocity one more time. So in this case, we can use our differential equation that models this situation. dv dt equals negative 0.04 times the velocity minus, and here since we're using meters as one of our units, we'll use the gravitational constant in terms of meters per second squared, and that'll be 9.8. Here, if I see this as one piece and I divide both sides by this, I'm going to get a separable differential equation in which I can integrate the left side. That equals 1. Integrate both sides with respect to t. Now this will be a similar u substitution as we did earlier in the video, so I'd recommend that you pause it and attempt it on your own. We know that this is going to be natural log as long as we accommodate for what would normally come by taking the derivative of this term afterwards. So it'll be negative 1 over negative 0.04, or sorry, just 1 negative, times natural log absolute value of the input let's multiply both sides by negative 0.04 to cancel that out. Now we want to know when does v equal 0. So normally we would solve this equation to get t by itself if we wanted to get a general explicit equation for velocity with respect to time. But in this particular case, we just care about using the velocity equation to help us identify the height. So we could at this moment solve for what t value gives us the velocity equal to 0. But as I'm saying that, I then recall we don't just want the time that it has the maximum height. We then need to find the maximum height, which means we need to find the position function. So at this point, let's actually do solve for velocity so that we can then have something that's easily integrable to find the position function as well. E to both sides will have us negative 0.04 v minus 9.8. Similarly to before, e to the c just becomes the constant c multiplied by e to this expression. Similar to our reasoning before, we can drop our opposite values. Now we can solve for v, add 9.8 to both sides, divide by negative 0.04, and we get, and then 9.8 divided by 0.04, 245, that should be negative. So I'm just going to combine our unknown constant with this negative 0.04, and we get c times e to the negative 0.04 t minus 245. So in order to find the maximum height, we're going to set our velocity equal to 0. I guess before we do that, we need to figure out what is this c value, and that's going to come from our initial velocity. So when t is 0, e to the 0 becomes 1. We get 49 equals c minus 245. Add 245 to both sides, and we see c should be 294. And that will give us our velocity equation. Now to figure out when this is equal to 0, we set the velocity equal to 0, and then we will solve to get t by itself. Let's just kind of verbally outline the steps, and then y'all can check it in your calculator. You would first move the 245 by adding it to both sides. You would then end up dividing both sides by 294, taking the natural log of both sides to get rid of our exponent, finally dividing that final thing by our negative 0.04, and rounding to 3 decimal places, we would get 4.558 seconds. Now we can use this time when we had the maximum height if we had our position equation. We know position is the integral of velocity, so we are going to integrate this equation once with respect to t, and that would give us our position with respect to time equals the 294 divided by negative 0.04 e to the negative 0.04 t minus 245 t, and then plus our constant of integration. Now we have some important information to leverage here. We know when time t equals 0, the position is 0. So we can use this to solve for c. Simplifying this fraction, we get negative 7,350. Now e to the 0 becomes 1, so that gets multiplied by 1, minus 245 times 0 is 0, plus c. We can see that c needs to be positive 7,350. So now we calculate the position at 4.558 with this new value for c plugged into our equation, and then rounding that to 3 decimal places, we get 108.280 meters. In our next example, we have a car that starts from the rest. So we know that our initial velocity is 0. The engine of the car provides an acceleration of 10 feet per second squared. So I'll be increasing the speed, while the air resistance decelerates for each foot per second of the car's velocity. We're asked to find the car's maximum velocity or its limiting velocity. So our idea here is to find an equation that represents velocity with respect to time, and then consider as t goes to infinity, how does velocity behave? And particularly at this point, once we solve our differential equation, get v by itself, we might be able to answer the second question without even solving explicitly for the velocity equation. Now the first thing that we need to do is we need to set up the differential equation, how is velocity changing with respect to time? And in order to understand that, we have to understand the two forces acting on the car's change in its velocity over time. One is that it is accelerating, so the speed is increasing at 10 foot per second squared. And then countering that is that we have air resistance, so a decrease in our acceleration of 0.001 v squared for every foot per second of the car's velocity. So the change in the velocity over time could be described as the positive acceleration minus the deceleration. Now as we begin to think about solving this differential equation, the first thing I might recommend is taking out a factor of 10 from both sides of this term. That will make this a nice 1, and we'll see what happens as we take out a factor of 10 from the other side. So we have our dv dt. I'm going to factor out a 10. I'd be left with 1. And now we have 0.0001 divided by 10. That should give us 0.0001. And one reason this is going to be beneficial is 0.01 times itself. So if I square that, I get this 0.0001, which means what I'm looking at here is a difference of perfect squares. That's going to be valuable to us because as I try to create this separable differential equation, I'm going to move everything involving v to the other side. I'm going to get 1 over a difference of perfect squares. Well, that's something I know I can factor, use partial fractions on, and then I'll be able to integrate the two separate pieces once I've broken them apart. And that particularly became apparent once I factored out the 10 because that gave me a 1 here, 1 squared, and then this is also a perfect square. So we'll divide both sides. And I'm going to just rewrite it as the difference of perfect squares while we're at it. Let's integrate both sides with respect to t. And then off to the sides, we'll do our partial fraction decomposition. Multiply both sides by the denominator from the left. That will clear it completely from the left, and then it will clear partially from the right, and we'll be left with a times 1 plus 0.01v, b times 1 minus that, so 1 equals Now we need to carefully choose v values that will isolate a and b separately. Now if I plug in 100, what that's going to do is 100 times 0.01 is 1. 1 minus 1, that's going to cancel this term. And then we're going to end up with 1 plus 1 times a equals 1. So that tells me that a should be 1/2. Similarly, if I choose negative 100 as my x value, or my v value, now the a term cancels, and we're left with 2b equals 1, b also equals 1/2. Now at this point, whenever we split this up, the 1/2 can be pulled out of both integrals, and in fact soon we'll want to multiply both sides by 2 to get it to the right side. But we're left integrating 1 over 1 minus 0.01v dv plus the integral of 1 over 1 plus 0.01v dv equals 10t plus c. Let's also multiply both sides by 2, and we'll get 20t plus c. Now the left side integrals, those are nice. U substitutions, we'll see that it'll integrate to be negative 1 over 0.01 natural log of our original input plus 1 over 0.01 natural log of this. Now this 1 divided by 0.01 is 100, so we can factor out the common 100 term here, and we'll end up with switching this since this one's negative. Let's divide both sides by 100. that should give us 0.2t plus still our constant of integration. And now whenever we have natural log same base being subtracted, we know that combines to dividing their inputs to a single logarithm. And then let's try to understand what's happening here and see if we can answer the maximum velocity without necessarily solving to get v by itself. So the key thing is first that t goes to 0. Now in this equation, where is t? T goes to infinity. T is here. 0.2 times something going to infinity is still going to infinity, adding no matter what the arbitrary constant is, the right side of the equation is approaching positive infinity. Now the left side of the equation is natural log of this expression. So we understand the natural log graph. The natural log graph looks like this. The natural log graph only goes to positive infinity as its input goes to positive infinity, because we have to keep increasing our input forever and ever for our output to be approaching infinity. So what that means is this interior must be approaching infinity for a natural log of that to be approaching infinity. So we need to ask ourselves, when does this go to infinity? Well, in its nature, this is basically a fraction. So we think about, when do fractions go to infinity? They go to infinity when the bottom stays relatively fixed and the top explodes to infinity. Or conversely, when the top is fixed and the bottom gets infinitely small. Now let's think about this. What would make the bottom go very small? And then we'll consider, what does that do to the top? Does that mean the top would stay fixed relatively close to it, or what? So if we're considering when does the fraction go to infinity, we're asking ourselves, when does the denominator go to 0? We can solve this and get the equation. Divide both sides by 0.01, and I believe we'll get v is 100. So this is telling us if v goes to 100, the denominator will go to 0. Now, if the top remains relatively fixed at this point, we can say that that means this fraction goes to infinity, and then natural log going to infinity as an input goes to infinity as an output. So let's verify. If v takes on the value of 100, what's happening to the top? Well, 100 times 0.01 is 1, so we have 1 plus 1. Our top is basically acting like 2, and our bottom is going to infinity. That means this fraction is going to infinity. And then natural log of something going to infinity goes to infinity. So from this, we've been able to reason that as t goes to infinity, the velocity must be approaching 100, and then our units, this is in feet per second squared for acceleration. So the units for velocity should just be feet per second. So this is our terminal maximum limiting velocity. Now we're asked, how long does it take to attain 90% of the limiting velocity? 90% of the 100 feet per second is 90. So we're trying to answer the question, for what t value is the velocity equal to 90? We can just plug 90 into our original equation and solve, so long as we first figure out what is the c value. And that's going to come from the fact that our car started at rest. So let's first find c, then we will solve to find at what time is the velocity equal to 90. So we plug in our initial condition. 1 plus 0 becomes 1. 1 minus 0 is also 1. Now, natural log of 1 is 0, so the left side becomes 0. 0 plus c, we see that c is 0. Now we need to solve the equation natural log, or ln, of absolute value of 1 plus 0.01 times 90 over 1 minus 0.01 times 90. That needs to be equal to 0.2 t. and we're looking for what t is. Now 90 times 0.01 gives us 0.9, so we have 1 plus 0.9, absolute value is 1.9. Divided by 1 minus 0.9 becomes 0.1. That's equal to our 0.2t. And now let's simplify our left side. 1.9 divided by 0.1 is 19. Natural log of 19 is that. Divide both sides by 0.2. And we should get time is about 14.722 when rounding to 3 decimal places. So it takes about 14.722 seconds to reach 90% of our maximum velocity, or 90 feet per second. Now before we leave this example, I do just want to mention one particular quicker way to solve for our velocity equation if we remember a particular integral formula. So of course you can always go back to using our method where we realized we had a difference of perfect squares, so then we use partial fractions. You'll get the same answer. But if we remember this integration formula, it'll be quite a bit quicker to get our final answer because we don't have to go through the partial fraction method of integration. If you see the integral of 1 minus 1 divided by 1 minus u squared du, then that integral is inverse hyperbolic tangent of u plus c. And then what we could have done there is once we got this integral, we would get 100, using our u substitution, 100 inverse hyperbolic tangent of 0.1v equals our 10t plus c. Then we could divide both sides by the 100, we get this equation, at which point we apply hyperbolic tangent to both sides. Hyperbolic tangent of inverse hyperbolic tangent just gives you your input back as a result. And then we can multiply by 100 and we get our equation. The velocity is 100 times hyperbolic tangent of 0.1t. And particularly, this method is useful because we have an integral formula for inverse hyperbolic tangent. So if you wanted to find the position equation for this particular problem, using this integral formula is going to get you to a much nicer velocity equation that we can work with, where we know how to integrate that again in a really quick known formula. So I'd encourage you to just keep this in mind. It can be helpful. It's a bit of a time saver, particularly if we were going to integrate again. We'd want to integrate in this format to look for position. Now, if you have any questions about this 1.8 material, please do let me know. Remember, it is optional, so it won't be covered on any upcoming exams or assignments, but I'll be happy to answer any questions you have. And if you'd like to test yourself, we have a handful of textbook homework problems assigned in our current week's module. Thank you.